In this video, we're going to introduce a new operation, so to speak, that can be applied to a function that will give us a radically different approach to solving certain initial value problems, right? And that transform is called the Laplace transform. And by itself, it could be studied, and it has been studied very deeply. In fact, you could make an entire course out of studying the Laplace transform and related transform. Now, before I give you the definition and look at a couple key properties of this transform, I just want to kind of step back a little bit and say that in your study of math up to this point, you have encountered certainly you've encountered the word transform before, and you've looked at certain operations that would transform a function into another function. So for instance, and I'll just use this as an example. I'm going to take my function, let's say, let f of t be something simple like t squared, right? In your first semester of calculus, you probably learned about the derivative, and you can think of that as a certain transform. So I'm going to use my magic box here. This is my machine that will do something. So if I put this f of t into my derivative, I'm just going to call this d for derivative. Or if you wanted to, you could denote it like this for your Leibniz, but using Leibniz notation. But if I were to transform this function using this process, then I would end up with 2t, just applying our derivative rule. Again, we don't necessarily think of it this way, but that's what a derivative is. It's a method, it's a set of rules that transform one function into another function, and we know that this result gives you a lot of meaningful information about the original function. But then you could also take your f of t and, in that same course, you probably learned about antiderivatives. So we could transform it using this process. And again, if I put this f of t into this magic box, I'm going to get out a 1/3 t cubed and then plus c, which again, we've seen the significance of this plus c quite a bit. But again, this result, right, the result of transforming t squared under this process, again, it gives us another function that holds other significant meanings, right? So there are lots of things we can do to change a function into another one, and then usually how popular one of these transforms become, it depends on how useful the result is. Well, it turns out in the context of differential equations, there is another transform that can be applied to a function such as this that will have a great significance in terms of usage. Like, we can use it to actually solve many initial value problems in a very different way. So what is this transform? So I'm going to write it down using my same box notation. But it's going to look a little different because it does involve an integral, but a very special type of integral. But it's not just an integral. There's going to be some other pieces to it. So let me now put some conditions on f of t. So let's say f of t is, I'm going to use the phrase piecewise continuous. And then later on, we'll kind of dive into exactly what this means. Let's say this f of t is piecewise continuous on the interval, let's say 0 to infinity. So we're only worried about the positive or non-negative real number line, right? So from t going from 0 to infinity. And so here's what we're going to do to kind of transform this function. We're going to do an improper integral from 0 to infinity, and not just of the function itself, but we're going to multiply the function by a special exponential function that looks like this. It's e to the negative st, and then we're going to multiply our original function by that, and we are going to integrate with respect to to t, right? And then it turns out now I can't write down specifically what this entire process, you can see it's a lot more involved than a derivative and just a basic antiderivative. So I can't write down what it would be, let's say even for this function, at least not right now. But the interesting thing is, you might say, well, how do I do this when there are two letters here? Well, just at this point, think of S as like a parameter, kind of the same way you think of the plus C, right? So you can kind of treat it like a constant, and you're integrating with respect to t. So what will happen is after you find your antiderivative and go through and evaluate the improper integral, which has its own process, and this s will still be a part of the answer. So what we're going to end up with is a new function, right? Just like how we ended up with new functions on this side, we are going to end up with new functions. And so it's not going to be the same as little f, so I'm going to call it big F. But not only that, but it is going to be dependent on s, not t, because we've integrated with respect to t, evaluated the improper integral. So all that we're going to have left at the end of this process is some function of s, right? And just looking at this little, without going into a lot of the details just yet, you can see that this third transform that I've written down is fundamentally different from the first two. Because when I transform something based on the derivative, I don't change the independent variable. It's still a function of t. Similarly, when I take the antiderivative of a function, right, I haven't changed the independent variable. But now with this crazy looking transform, not only do we change the operations in the function, but we've also changed the independent variable from t to s. And in many engineering applications, that change alone is huge, right? Okay, so this third example here is what we refer to as the Laplace transform, right? So this is what we call the Laplace transform of little f of t. And because Laplace is the last name of a famous French mathematician, since his last name starts with the letter L, just like how we have a D for a derivative, and now we have this kind of elongated S, I like to call them seahorses for antiderivatives, we have a symbol for the L, and it's kind of the script L. So it's kind of like that. And then we use braces for whatever reason, and we put the original function inside there, and then we end up getting this new big F of little s there, right? So that's the Laplace transform. But again, because of the improper integral in the definition, we have to be really careful in how we evaluate it. And also, you might remember when you studied improper integrals that not every improper integral led to what we call it convergence. So there are some improper integrals that diverged. Well, what does this mean for our Laplace transform? Well, we're going to give a couple sufficient conditions that will guarantee when when the Laplace transform will always converge, right? And the problems that we will work with, everything will work out nicely, all right? So that's our Laplace transform. Let's actually do a really simple example of the Laplace transform just to show you the process, right? But what we're about to do now is not the typical way that you would approach the Laplace transform, and we'll see this in previous, in successive videos. But let's do a little example here just to see, and let's take a really simple function. Let's just take a constant function, f of t equals 1, and what we want to do is we want to find the Laplace transform of f of t. Right. Okay, so we're going to write down our definition. So I'll just say this. The Laplace transform of 1 is the improper integral from 0 to infinity, and then it's e to the negative st, so it's s times t there, and then times 1 dt, right? So there are a couple things that we have to remember. First, we have to remember how an improper integral is defined. Now remember, an improper integral is defined in terms of a limit. So there's another operation, right? So this is the limit. Usually we use b for the upper limit. B goes to infinity. And then we take the integral from 0 to b. And then when I simplify what I have here, my integrand, the exponential times 1, that's just the same exponential. And then this is dt, and it looks like that, right? So the process is we evaluate what we have in square brackets first, right? Whatever integration technique that we have that applies, we're going to apply this. Then we apply our fundamental theorem, and then at the very end we take the limit. So let's do that in those 2 steps. I like to do it in 2 steps. So step 1, we're going to evaluate the integral from 0 to b, and then it's e to the negative st dt. Now how do we do this? Well, as I said earlier, the s here, you can think of it as a parameter, as a constant, but it doesn't have a fixed value, right? And depending on the value of this s, it might actually affect how and when the integral converges. So right now, what we do is we're going to treat s as a constant. That's what it is. We can't, because we're integrating with respect to t. So we treat s as a constant. All right, let's see what happens. So if, for instance, we had a 5 here, or a 2 here, or let's say a negative 5 or a negative 2, when we integrate this exponential, we end up having to reverse the chain rule and divide by whatever this constant is. So that's what we're going to do. So we're going to get back the e, but then we have to divide by the negative s, right? And then we're going to use our fundamental theorem from 0 to b. Now, because this negative s that's in the denominator, I can treat that as negative 1 over s. I'm going to do that. And then in parentheses now, I'm going to put the evaluation when we plug b in for t, right? Because remember, we're integrating with respect to t. This is the upper limit for t. So we end up getting e to the negative s times b, and then minus the evaluation of the exponential at t equals 0. Well, that's nice. That works out to be e to the 0, which is 1. So if I go ahead and distribute the negative 1 over s now, we're going to end up getting negative e to the negative s over b over s, like that, and then plus 1 over s. All right. So that's the first part of the evaluation of our improper integral. Now we're going to take a limit of this as b goes to infinity, right? So let's see what happens. The limit as b goes to infinity of what I have there, negative e to the negative s times b over s plus 1 over s. Now, again, when we look at our limit, b is what's going to infinity. So s isn't changing per se, right? We're just asking ourselves what's going to happen to what's in the parentheses as b goes to infinity. So the 1 over s, again, is treated as a constant. So that stays the same. That's going to be there. Now, as far as the exponential function is concerned, exponential functions, these basic ones, they do one of 2 things as b goes to infinity. Either they go to infinity or they go to 0. For them to go to infinity, the exponent has to come out to be positive, right? In other words, you'd have to have e to a really big positive number for that exponential to go to infinity. In fact, let me write it over here kind of as a couple conventions. So if you have like e to the infinity, right, positive infinity, that goes to infinity. Whereas if you have e to the negative infinity, that goes to 0. So the only way this limit is going to converge is if we can ensure that the exponent ends up being a large negative number. Now, b is going to infinity, so we have that right there. So we would have to ensure that s is positive, and then the negative sign in front of it would make the entire exponent negative infinity. So this term right here will go to 0 provided s is greater than 0. So this is what I'm going to write down. So here's our limit. So it's going to be 0, and I'm going to put the condition under it. So this is whenever s is greater than 0. So that's the first term. And then plus, we know the 1 over s. Again, since s is being treated as a constant, then it looks like that. So as long as s is greater than 0, the first term is 0, and then the limit is ends up being 0 plus 1 over s, so that's 1 over s. Right. So here is our summary now. So if f of t is equal to 1, then the Laplace transform of f of t is equal to 1 over s, provided s is greater than 0. Right? So we could write it like that, or we could use the big F of s notation like this. Right? Yeah, so this strange way of transforming functions changes the constant function 1 into 1 over s, right? And again, you might ask, well, what is the significance of this? Again, we're going to explore the significance later on. Here, we're just introducing you to the idea of this special kind of integral transform, right? Now, I'm going to state a couple properties of the Laplace transform, and then we will pause this video and then pick up further work in the next few videos. So it turns out that because the Laplace transform is defined in terms of an integral, then it has certain key properties. And here's what I'm just going to write it down. So suppose we have f of t and g of t. Suppose we have two functions now, and let's say these are both, again, piecewise continuous on the interval 0 to infinity. So these are piecewise continuous on the interval 0 to infinity. And then let's say, I'm just going to use alpha and beta. Let's say these are real constants, right? So these are real numbers. Well, it turns out that the Laplace transform of a linear combination of these two functions. So if I take alpha and I multiply f of t, and then I add to that beta times g of t, because we define the Laplace transform as an integral, we can split this into two separate integrals, and we can factor the constants out of the integral. So two things that we do we take for granted when we do integrals, that also works for the Laplace transform. And this is going to be, again, another powerful property. There are going to be a few properties that we introduce before we get to see how this all relates to differential equations. But the property is, this is alpha times the Laplace transform of f of t, and then plus beta times the Laplace transform of g of t. And again, let me just use this to enforce another way that this can be written. So when I transform little f of t, I know I get uppercase f of s. So again, when you use just the letter to indicate the Laplace transform, it's the Laplace transform itself is always the uppercase version of the original function. So you can think of the uppercase f of s as the image of little f of t under the Laplace transform. So if we transform little g of t, we're going to get an uppercase g of s. So then this becomes beta big G of s, right? And this, you might remember, is actually, these are properties of linear transformations. So it turns out that the Laplace transform is a linear transformation, and we like that. So that means that this is a linear transformation. All right. So this is all I wanted to do in this particular video. Introduce this new transform, do one very simple one, and then again highlight this key property that will make our work a lot easier. And there's several things that we're going to introduce that will actually make our work easier, but we will eventually get to the point where we can use this really powerful transform to do something interesting with our differential equations. So I know you're interested in seeing how that works, so hop on over to the next video. I'll see you then.